energy technologies, and specifically how process systems engineering can help us answer some questions in this area. So, we are interested in studying these systems. I would say, maybe some years ago, I would have stressed also fossil fuel reserves. Maybe that's not the case anymore. But still, even if that's not the case, we would still want to explore these new energy systems for environmental concerns. And this obviously has been recognized by many experts and in many different fields, and a lot of technologies have been proposed to.
I'm sorry, Professor, for interrupting you. Can we take your permission to record the seminar?
Yes, of course. Yes.
Thank you, and sorry for interruption.
No problem. So this has been recognized by many experts in many different areas, and therefore many different technologies have been studied, and I'm listing here some of them. Including use of conventional resources in new ways. For example, natural gas to chemicals, that would be one. Trying to improve older renewable technologies, but also come up with new. But despite all these research, let's say in the fundamental questions, there are some high-level questions that remain open. For example, if we were to go to fuels, would it make sense to do it from electricity or biomass? Just to stay with biomass, should we just gasify biomass and then do something with the syngas, or should we try to convert sugars of biomass to liquid fuels directly, and so on and so forth, right? Many different questions. So really the goal of today's talk is to try to convince you that process systems engineering can help us address some of these questions, if not address, help us think about some of these big questions. So this is the outline of my talk. I'll start a little bit with an overview of the methods that we are developing in order to address some of these questions. So the methods are in the broad area of process synthesis and analysis, but I'm going to focus on synthesis. And then I'll just go to applications, and I'll discuss three applications: biofuels, solar fuels, and then solar power with emphasis on storage. So let me start with process synthesis. And at a high level, there are two schools of thought in process synthesis. One is where we decompose the problem into easier problems. And this is a schematic, a very simple schematic. At the very heart of any chemical processing facility, there should be a conversion, a chemical reaction. So the idea there is to come up with a design for the reactor network. Once we have made these decisions, obviously we will need separations, because in real systems, for example, conversions will not be 100%, selectivity is not going to be 100%. We will need to design a separation network around that. Then once we have made our decisions about reactions and separations, we would have some heating and cooling duties, distillation column, we would have both of them. How do we then do heat integration? So around that, we're going to design our heat integration and potentially utility system. So this is very intuitive way to think about this problem, and very elegant, and can be very effective, because the problems are easier, but it does not account for interactions. And the example that I often use is that when we are trying to, for example, maximize selectivity in a reacting systems, we may do that, but we may lead, by maximizing selectivity, we may lead to the small production of a byproduct, which forms an azeotrope. So although from a reactor standpoint, this is a good objective function, if we think about the entire system, that's not a good objective function, because you have an azeotrope, our separations network now is going to be inefficient. So what's the alternative? The alternative is what we call superstructure optimization, where all the options, although I'll come back to this, this is not a straightforward exercise to find all the options, but in principle, we would have all the options mapped in a superstructure. So here I'm showing, just again, to illustrate the points, very simple decisions. We're going to install a CSTR or a plug flow reactor. So we're going to choose one of them, and we will either use a sequence of distillation columns or an adsorption or membranes. So all the options are there. So it's not a process flows diagram. It's a network, parts of which are going to be activated and deactivated. How we're going to do that? We're going to generate a model that is different from a traditional process model because it has the discrete decisions, binary decisions, these Ys. And these Ys, if we can solve this model, which I have written here, will tell us which of these units are going to be active in the optimal solution. And then for the units that are active, we're going to calculate as we would normally do process flows, temperatures, pressures. So this approach appears to be very powerful, but it has a big, big challenge, and this is the computational issue. So in the next slide, I'm just going to show the equations that this process simulator would automatically generate if we were to perform a simulation, right? And they are not meant to be understood, all these equations. I just want to convey the complexity. So it's a multi-tube reactor for methanol synthesis. For the students in the audience, we maybe just draw our unit in Aspen or the preferred simulator. What is it really behind it, right? And if it's a detailed simulation model, we would have lots and lots of equations like material balances, energy balances, kinetics, if we want to account for pressure drop, hydraulics, and so on and so forth. And as if that was not enough, some of these letters here, right, they are enthalpies, reaction rates, molar volume. So they are coming from additional equations, thermodynamics or kinetics. And the last point is that these kinetics, which actually in this case reverse water gas shift, the kinetics would look something like this. We would have these partial pressures in the denominator. And when partial pressures go to zero, numerical stability issues and all that stuff can happen and hinder the solution of the use of these models in an optimization framework as opposed to simulation. So what can we do? Simplify these models. And the idea is not ours. It has been around for many, many years. Here we are just applying it in energy and processing systems. So the idea is to get a complex model. Here, what I'm showing is all the variables that we need to have in order to calculate how our system behaves. An example would be in a distillation column, we would have to calculate compositions, flows, everything in every single tray, and replace these models with really a reduced version where some of the variables that are not of interest from a process synthesis point of view, where we're connecting different units, are removed. And it's an approximation, so we have to sacrifice something, but allow us to solve bigger problems. So using again distillation column as an example, if we're thinking about a system that has 10 or 20 different units, maybe knowing what is in every tray is not that important. What is important is the feed of the distillation column, what comes at the top, at the bottom, and the heat duties. Okay, so I'll go through this slide very fast. I'll be happy to come back later. There are two things then we have to do. Design this surrogate model, this approximation. It's not a completely straightforward question because we're going to remove, in the previous slides, I showed that basically we remove some variables from the original model. What we are left with should behave well numerically, should not be singular. And this turns out to be a graph theoretic problem where we form a graph with different variables and different equations. We solve this problem, and the solution of this problem is going to tell us what the right variables, input variables should be. And from these input variables, we calculate the output. The second question then is, how do we write this model? And we should not replace everything. This is a reactor model, and I'll just go through the first two equations. This first equation basically says what comes out of the reactor. This is a summation of from all the flows are equal to the flows that go in plus stoichiometric coefficient times conversion. So this equation is very simple, very intuitive, and we don't have to replace it. What's the tricky part? That this conversion of its reaction happening in the reactor can be very tricky. Energy balances, similarly, relationship about temperatures, we don't have to replace them. What we really have to replace is this conversion, because this conversion is going to depend on kinetics and it's going to be complicated. Once we have made these decisions, then it's a fitting exercise. I'm not going to go through the details. We can use different fitting methods. Artificial intelligence is very trendy. We can use the preferred method for developing these simplified models based on data that come either from simulations for a given unit or from experiments. And actually, in our experience, and I will be describing later in my talk, a lot of systems that we have studied based on experimental data coming from collaborators. Okay, so we have done that. We have simple models for each unit. Are we done? Unfortunately, there is one more step, and that's where now the challenges, the optimization challenges come in. I'm illustrating this through an example where let's assume for the sake of simplicity, I have 3 reactors, and somehow we have developed a model where we have only 2 input variables, x1 and x2. Okay? But we still have to select which catalyst we're going to use in this reactor. If we go with catalyst 1, this is the objective function. Let's say we're minimizing cost, given certain output. It is a very easy problem, right? It's a feasible region that is convex, a single minima. Even if it was like this, it would still be an easy problem. But maybe the feasible region is not convex. It has this shape, which means that we have 2 minima, or the objective function has multiple minima. And really, the problem we are trying to solve pictorially is something like this. We have to first pick the problem we want to solve, the reactor, and then for this reactor, solve the optimization problem. So this is challenging, and really the group is trying to develop methods to solve these problems. This is my last slide on process synthesis. So in general, what we would like to do, we would like to develop good methods for solving these process synthesis problems. And as you will see later, one of the reasons that we want to develop these efficient models is because we want to solve lots and lots and lots of optimization problems. Because this is for preliminary studies, right? It's not to build a facility that is going to be utilizing, let's say, the latest solar thermal technology. It's more to get the results that would allow us to understand these systems better. And to understand the systems better, we have to run many, many optimization under different scenarios to really understand the drivers. So that's our goal. What I described very briefly is that we can think of it in 2 ways. One is develop simpler models. And I will be showing later that in our favor, sometimes models are sufficient for these preliminary studies. And then that experiments also can be used to develop these simpler models. That's one. And then at the second level, assuming we have these simple models, we want to develop good optimization methods for this class of problems where we're making discrete decisions and continuous decisions. Okay. Let me now go to the applications. So the work has worked a lot in the area of biofuels, but I chose to focus more on solar systems. But I still wanted to discuss two examples. The first one is just to illustrate how superstructure, let's say, real case, a real system of experimental results. So how we can use superstructure synthesis to think about the system. So this is a pre-treatment of biomass. So biomass is harvested, is brought to the biorefinery, and the first step really is to break this very recalcitrant, this very resistant mixture of lignin and polymers of sugars, right? So a colleague of mine at the University of Wisconsin 5 years ago now, has developed a series of pre-treatment technologies. And this is a very, very nice system from a basic science standpoint and a catalysis standpoint, because we are using GVL gamma varylolactone, which is a solvent that can be made from biomass, as the solvent to really carry out this pre-treatment. So it's very efficient. It has received a lot of attention, but the downside is leads to a complex separation system problem. Why? GVL here is our solvent. So somehow we want to recycle it, right? We want to be able to using it again. Sugars is the valuable, let's say, intermediate, or the most valuable intermediate, because it's what we want to convert finally to a chemical or a fuel. Lignin, we also want to separate it from everything else because it can be used to generate power. So how do we carry out this separation? One option, experimentally found, is that we can add salt. And if we add salt into this system, we're going to have two phases. One is going to be the aqueous phase, which is going to have sugars and primarily water, a little bit of GVL. And then the other system that is going to have lignin, the organic system that is going to have GVL and lignin. And then, I'm sorry. And then the second, so that's one option. The other option would be to do it with supercritical CO2. The idea here is that we're going to use supercritical CO2, and we're going to form again the interesting phase, GVL and sugars, and then another phase that, so here we're going to use CO2. CO2 is going to be recycled, and this one is going to have primarily lignin. There is another option with a different solvent, and all of them, they would really, and then another option with where we're using an absorbent, activated carbon. Okay, so we have 4 different options to get our sugar stream, and then still we have to separate water from lignin. So there are more options, for example, here, lignin adsorption from, GVL from lignin. So more options for this separation. So at the end, when we put everything together, this is the superstructure for the separation network. Using surrogate models based on experimental results, these types of superstructures can now be solved. Just one example. For the very first part, which is the pretreatment, actually the pretreatment, I described it a little bit simplistically. It has a number of steps, but from a synthesis standpoint, this can be viewed as a block. And what is it that is going to impact what we get out of this system of reactors? Well, again, our collaborators from the domestic group told us that and I'm rewriting here the equations that I had written earlier. The flow of what comes out is the flow of these two streams, what goes in, plus the hydrolysis of the two polymers. And this hydrolysis, the gamma stoichiometric coefficients are known, these flows are known, if we are thinking about being parts of the input. These conversions really are a function of the solvent that we're using. So this was an example of a surrogate building from experimental data. Once we have this process network, separation network, we can start thinking about utilities, about heat integration, and the other parts that I described earlier. Okay, so I went a little bit through the detail. I won't be doing that again. I will be just now start presenting results directly from different systems. Last slides on biofuels. In the States, there has been a lot of discussion about what are good strategies for converting biomass to fuels. And the Department of Energy and others have suggested that what we really have to be doing is maximizing carbon yield. So we wanted to really test this hypothesis, whether the best criterion for choosing these strategies is maximizing carbon yield. That is the carbon in the final fuel given a fixed amount of carbon in the input. So to do that, there are 2 systems. One is the very traditional ethanol, biomass to ethanol, and then another one, which again was based on experimental results from our collaborator, Professor Domesik, was going to alkenes. So these would be hydrocarbons, basically using chemical catalysis. And at a very, very high level in these 2 slides, in these 2 figures, panels A and B, I'm showing that just the final results. At a very high level, we see that if we are producing ethanol, we start from 1 ton, which has a certain amount of carbon in the 3 major components. And finally, we get 159 kilograms of carbon in the final product, in ethanol. If we start with the same amount, we do all the analysis, the inside, we are not interested in what all the details. Finally, we get 130 kilograms of a different fuel though. So based on this, again, which is also in reports of in the Department of Energy, one would think that the biochemical conversion, BCE, is more atom economical and therefore it's better. But is it better, right? That's what we want to really understand. So I'm going to be showing in the next animation a different figure. It has the same reference, but we are thinking about energy flows, not carbon flows. And we would like, when we are calculating these energy flows, also to think about excess electricity that can potentially be produced in the biorefinery, because remember, lignin can be burned to produce electricity, and also the final use of this fuel. So again, same, here we have 1 ton of biomass as the starting material, but everything else is energy flow. We are producing this amount of energy in the form of ethanol, still more energy than in our liquid fuel, but two big differences. One is that one of the reasons that this yield is lower is that some residues cannot be converted, in this case to fuel, but they get burned. So if we think now, this biorefinery produces more excess electricity, which is going to be used, just to keep the same reference, by an electric car. The electric motor has higher efficiency. So finally, if we do the calculation in terms of total mechanical energy, which is a better, let's say, equivalent of the fuel that would be displaced, we find out that this is a better option. This biorefinery would displace more fossil fuel than this biorefinery. Okay, so the conclusion of this study really was that it's not only the carbon yield, but it's also the biorefinery efficiency, because this is reflected in the amount of excess electricity that we're producing, and the fuel quality that have to be taken into account when we are deciding what conversions to make and what strategies to adopt. Okay, so let me now switch to solar fuels. I think you live in an area where you know very well that solar energy is abundant. These are some of the statistics that one can find very easily. These very staggering actually numbers when you do the comparison, but the picture is not as rosy for two reasons. One is that converting this amount of solar energy to electricity or fuel has low efficiency, and then also we have a lot of intermittency. Day and night are very different. Cloudy day, winter, summer in many parts of the world are very different. The day, weather, and all these things. So, what we would like to study in this part of the talk is to understand how to use solar energy to go to liquid fuels, not electricity. Now, just to set the stage a little bit and put everything in context, if we ask the question, how is best today to use solar energy to go to liquid fuels, and many papers have shown that, this is not our calculations, it seems that this is the best way. We still go through electricity, but then we use excess electricity to do electrolysis. And then once we have hydrogen, we can go with hydrogen to liquid fuels. This pathway has an overall efficiency of roughly 7%. 30% photovoltaic, 80% electrolysis. These numbers are rough. You may disagree, but they give you a rough idea of the pathway of the efficiency of this pathway. Now, so before we continue, an interesting observation is that if we stay with electricity and we use storage, we are not talking about cost right now, right? Just efficiencies. Actually, using it directly in an electric motor has higher efficiency. But we still need liquid fuels for planes, heavy trucks. So the question is, given that this appears to be the best today pathway to liquid fuels, what would it take? So a direct conversion of sunlight to liquid fuels, how good should we make this direct conversion to compete with the current pathway? So what would it take to reach, let's say, 3 to 5% efficiency in this direct conversion? I'm saying 3 to 5 because I haven't accounted for the conversion of the incorporation of the renewable hydrogen into a liquid fuel. So we would like to study this really direct conversion, which is not so direct, is not a simple block. The idea would be to have what we termed a solar refinery, where we would use solar to generate utilities, heating and electricity that may be required, for example, for pumping, but not for the chemical conversion. There are many different technologies that have been proposed for these direct conversions. We are not going to focus on the specific technologies. We want at a higher level to ask how good should these conversions be to reach this type of numbers. And then potentially CO2, the carbon can be coming from capture, the water can be coming from other sources. Okay, so very simple now. This is the first iteration of the process. We capture CO2, we reduce it, yellow because here we're using solar energy, then we will have water, for example. In all these systems, it appears that we are generating some water. So we need some gas liquid separation. If our product is methanol, which we're going to use as a model compound, we would also need this separation. And then we would need also gas liquid separation. Okay, sorry, gas liquid separation and then products by byproducts. This, of course, is the tricky part, right? This solar-based conversion. We went to the literature. This is now a few years old, but I believe that these numbers are still relevant. 5% conversion of CO2 and 40% selectivity to our methanol. Actually, I would say these are probably optimistic. We do a very first energy calculation, and we realize that if we assume here that I'm producing 1 kilogram of methanol, and I just back calculate all the flows and the energy requirements, this is the picture. Which, let me explain, it is not very good. This is the heating value of methanol. This is all the energy that we require to run this system. And why this black bar is so big? Because we are spending energy to capture CO2. With 5% conversion, then we let it go. But we're chemical engineers, and you will tell me, what are you talking about? We have learned about recycles, and you will be correct. So let's do the calculation with recycles. It is much better. It is much, much better because now we don't let really CO2 escape to the atmosphere. So the black bar has become very small, still not insignificant, but now we need energy to carry out these separations. But still, we are getting there, or we're getting closer. At this point, we are spending 7 times more than the energy that we are producing, but we have started at these low numbers. So then the question is, what advances are needed in catalysis and reaction engineering to make this system better? Okay. One note about the metric that I will be using. I think what sometimes is not thoroughly appreciated, that we should have a common energy basis. So here one could say, okay, we do the simulation, optimization, we get out our flows, temperatures, we calculate heat and electricity required to run this system. And we compare this heat and electricity with what we are producing here. It's not exactly the same, right? Because these energy numbers are not the energy that should be included in the fossil fuel that would be used for electricity and heat generation, right? So really what we have to be comparing is high heating value, let's say, of our fuel versus this. And there are these efficiencies that should be taken into account. Now, if you remember, I said that we can also use those solar energy to make heat or electricity. So at the end, this is the big picture. We could be choosing between these two, how we want to generate this, but we will be using solar energy for the conversion, for this photocatalytic or thermochemical conversion. So the metric that I will be using, it won't be efficiency. It's a little bit, for a lack of a better term, we were not very creative with this term. We call it energy incorporation efficiency. So really, it's the energy, high heating value of our renewable product minus the fuel that is used, if it is used, to run this system, divided by the high heating value of our renewable product. So this can be negative. This number can be negative. If it's positive, it's good. And the highest it can be 1. Okay, so let's see some results. This is the, and maybe another thing that I want to bring to your attention, the energy present in 1 kilogram of methanol is roughly 23 megawatts. So this is the energy requirements to run this facility as we increase conversion and we change the energy required to capture CO2. So as expected, we see the energy decreases as we are moving here. Better catalysis, better conversion, and the capture of CO2 is done more effectively. We should be in this region for the system to make sense from an energetic standpoint. If we can start using the byproduct, this boundary is moved, but for now we are going to focus here. So this graph is obtained by running one optimization for each combination of conversion and capture cost. And so this is the result of thousands of optimizations, and that's why I want these methods to be computationally effective. Okay, now we can overlay, and I think what is interesting, current separation technologies for capturing CO2 in terms of energy. So this is a little bit, the shades are not that clear. I hope you can see. Chemical absorption, MEA, amines, is probably the front runner. Why is the front runner? Because of cost, not because of energy, right? So if you want to capture, I would agree that probably amines is the best technology, but from an energy standpoint, it's not great. There are indications that some other technologies may be better from an energy standpoint. So they definitely should be studied, though the cost should come down for them to become competitive. Okay, so this was in terms of energy. I want to show also some numbers about cost. What we realized very soon is that this block 2, the yellow block, which was about the reduction, it is very, very expensive. The activities of the catalysts are very low. We would need very big reactors. The reactors would be expensive. The catalysts would be expensive. So this is definitely the driver. So we're going to ignore that part for now. We have some publications that we studied that, but for now I'm going to ignore to keep it a bit simpler. So what we are showing here is again the results of multiple optimizations, many optimizations, where we are calculating the selling price of the renewable product as a function of selectivity and conversion. Now, the minimum selling price can be viewed as the break-even price. So it's the price at which we should be selling our product to just cover our expenses. So the higher this minimum selling price is, the worse the system is. We want low minimum selling prices. That would indicate that we are breaking even without selling the product at very, very high prices. So this is when we did the study, that was the industrial price. For this system, without accounting for the reduction, the minimum selling price is 1.87, which is actually very good. Actually, it's very, very good because, again, that's renewable, but we do not account for the reaction. What is interesting, though, so 1.87, it's roughly, I don't have the scale. I'll have it scale in the next. Let me, for example, 187 is roughly this area when it becomes green. So we are here, right? And the cost, we become competitive with a 0.6 number. 0.6 number is roughly the third shade of blue. We are in this range, we become competitive, okay? From a cost standpoint, oops, we are not, though, renewable there. Why? Because given these selectivities and conversions, the energy to run this binary would be more than the production of methanol. So this demarcation indicates under what technology advances this system would be renewable, i.e. the pumping and the heating for the distillation columns and all that would require less energy than we are producing. What can we do? Start replacing, let's say, natural gas-based heating with solar heating. So this figure is exactly the same, but what we have done is we are saying every point should be renewable. So now for the same selectivity and the same one-pass conversion, basically the color has become more red or green. It has become more expensive. Using solar utilities and electricity made the system more expensive, but from an energy standpoint is more favorable. And now for the base case, the cost went up. Okay, last part of the talk. Solar power and storage. So we're going to be using concentrated solar power, although it could be used also with another technology for the production, let's say parabolic trout or other systems. We want to think how we can use solar energy when the sun is not shining. So we have seen probably some forms of this graph where the storage, the production in many years, in some years in the future, not that many, may exceed demand. So 2, 3 p.m. in the afternoon, maybe we have more solar than we need, but we have no solar at 6, 7 p.m. when people go back home and they're using air conditioning and the demand goes up. How can we take this surplus and use it later? And we are going to be using to kind of an exotic system. We are not obviously the first to think about this problem. Photovoltaics combined with battery have been studied. Concentrated solar power with 2 tanks, where we are basically during the day, we are generating a very hot liquid and we are using it during the night, has been studied. What we want to understand a little bit better here is thermochemical energy storage. So we are running an endothermic reaction when the sun is shining. We are producing a high energy content product or mixture of products. And during the night, we run the reaction the other direction. We are producing heat. We're using that heat for electricity production. So that's the idea. And this idea leads to a very interesting process synthesis problem. It's a very interesting process synthesis problem because it's not the typical problem where we are thinking about a nominal operating point and then we rely on control to keep us there in the steady state. We have 2 completely different modes of operation. During the day, we run the endothermic reaction. We are producing our products that are going to go to this other reactor, run in the reverse order, generate heat, is going to be used for power generation. But at the same time, during the day, we have over-designed the system. We are producing these products and we store them here. Also during the day, since this is over-designed, we have to use what was stored from the night to supply our reactor. So really during the day, this is emptied, this is getting full. And during the night, no more solar energy. This is full though. We start sending our products of the endothermic reaction to this exothermic system. We are keep generating heat. A and B is getting stored here. So early morning hours, this is full, TK1 is empty. So this is a very interesting system. I'll just spend one slide explaining why this in a way leads to a new type of process synthesis problems, because we have uncertainty, we have variability, right? And if this is the nominal operating point, a lot of research has been done around designing systems around a nominal operation, right? The feed may not always be the same in terms of amount and properties. The specifications may be changing. So a lot of work has been done around designing around a nominal point. But here, we have a very different situation where really we have to design 2 different systems linked together. So we have the day operation and the night operation. They are very different, but they are linked. They are linked through these tanks. And the power needed to compress the material that is being generated. So, and there we have a profile of the pressure in these tanks and also the electricity required to achieve these pressures. Okay, so how do we do it? We use a technique that is called stochastic programming to account for variability. Right? Summer and winter are not the same. both in terms of solar irradiance and duration of the two modes. So we generate these scenarios to represent an entire year. For each of these scenarios, we generate two modes. We generate, so this is shown here. For each scenario, we have day and night. Again, different days and nights in the different scenarios. And now our design decisions is what do we pick and how we operate in different scenarios. So these are, in this work, we just used 6 scenarios. We felt that it was representative. These are the solar irradiance during the day over 360. This is the scenarios that we used. And then we approximated a given profile through a night and a day mode. Directly results. The chemistries that have been studying the most are gas phase chemistry. So from ammonia going to hydrogen and nitrogen and back, and then methane and CO2 going to syngas and back. This is the levelized cost of electricity, so the lower the better, for the two-tank system and the two chemistries using pressure vessels and underground storage. Underground storage is, I would say, maybe a little bit of an ambitious idea that we can use underground caverns to store these systems. I don't know how feasible it is, I have to say that, but we just wanted to include it in our analysis. And it turns out that these systems, so when we are using really gaseous products, are not competitive. The reason is that we need so much energy to compress the system, and the compressors and the tanks are expensive. I'll just show here the big picture energy flows. If we start from 100 units of solar, we finally produce 15 units of electricity, but 2 have to be used internally for compression. And the costs also for these systems are significant. If we focus on, if we assume that underground storage is doable, it's feasible technologically, then we would be in par with two-tank systems. Just to make the point that we can also get these different levels, turbine outlet level, compression, and all that in our different scenarios. So in the hot days, we meet our target. As the irradiance during the year is not as high, then we may fall short of our nameplate capacity. Few more slides if I have the time. Well, do I have the time, or I can stop here?
Yes, Professor, we still have like 5 more minutes.
Okay, so I think I'll need only 3. So the challenge for what I just presented was the fact that we were producing gaseous products. So it was syngas what we were storing, and we need a lot of compression. So it's a trade-off, right? Big volumes if we don't compress of the vessels, small volumes if we compress, but then we have to pay for the compressions and the electricity. But there are some work out there where the reaction is very different. They are using oxides, which are solid. So we have here an oxide, highly oxidized, and it's getting reduced. And we're producing another oxide, less oxidized, which is still solid, and only one molecule, oxygen, for example, of a gas. So these systems have the advantages that we won't require so much storage, and also the reaction temperature can be higher. So the question is, very similar with the system before, but our system, the reacting system, is different. That is has an advantage, but because our reactors are solids now, we are charging and discharging during the day and night. So really it's a PDE that we have to solve. The profile in a solid bed, reactor bed, would be changing during the day and the night as we are charging and discharging. So it required the development of some surrogate models that I discussed earlier. I'm going to skip that. Once we had the simplified surrogate models, we could then plug them into the optimization problem that I described earlier to solve and get some results. So this is the last slide with results, and I'll go to the conclusions. Again, I'm showing energy flows and efficiencies of the different parts of integrated solar concentrated solar plant with thermochemical energy storage using a solid system. Efficiencies in gray for collector, receiver, storage. This is where we focused. And then finally the turbine. Maybe the number that is most interesting is this overall efficiency from collector to turbine. The 2-tank molten salt is 0.2. Now we see that we can reach similar efficiencies, overall efficiencies. This is one combination of material, one system, reacting system. Again, you see that we are producing oxygen. We can be producing water, which would be gas, but then with the storage, we have some advantages, and also CO2. And we can see that when we are going to solid, I haven't discussed cost, right? There are some other challenges there, but if we are using solid gas TCS systems, then the efficiencies can be as good as the 2-tank molten salt without using the underground storage. So let me finish with some concluding remarks. I hope I was able to show that synthesis, process synthesis and analysis can aid in addressing or help us think about some of these high level questions for energy systems. Very nicely, studying this system also, and we appreciate that and we enjoy doing that, is that when we are studying these new systems, some new problems arise which require the development of new methods, and we have been having fun with that. And then maybe some final thoughts that in a way we have evolved over the years about these questions is that sometimes asking the right questions is the most important step. Like, for example, calculating some of these energy efficiencies, and these were things that we were not doing, but we finally, we slowly understood that this is critical. Develop models from limited experimental results is very, very important, and how to do that, and because the groups that we are collaborating with cannot be generating, just data for us to develop our models, right? So this is an important step, and learning how to do it is important. And then finally, it's also important to quickly synthesize and evaluate new systems, because research moves very, very fast. If we want our analysis to have some impact, then we would have to be able to build these models, get the results fast, so then we can have like an iterative procedure where the insights then are used for the design of the next steps. This, I want to acknowledge the group. All the work, of course, is done by the group members. This is the latest photo from a Zoom meeting. This is, I think, what is going to be happening for some time. And then also some collaborators and financial support. And I would also like to thank you very much for the time you took, and I'll be happy to take any questions.
Thank you so much, Professor Maravelias. That was a very interesting and nice presentation. Thank you so much. So with that, let's start our questions. So Dr. Ali Al-Awami, go ahead, please.
Okay, thank you, Dr. Al. Thank you very much, Professor Christos. It is an amazing presentation. So my background is electrical engineering, so I'm an outsider here. Now I'm teaching a course in electricity and hydrogen infrastructures and how they are interacting. And well, this is the first time this course is offered in this new hydrogen mobility concentration that chemical engineering is leading, with Dr. Weil as lead of the concentration. So I'm learning along the process. Now, I'm going to give my students tomorrow a case study at which I need to convince them that in order to go from the very sophisticated chemical modeling into a workable optimization model, we really need to simplify things. Okay, so I'm glad that some of my students are actually attending, so it makes my life easier.
I'm glad I was able to help.
Yeah. So my question is, when you go in your process, going from the very detailed chemical modeling to the very workable optimization models, what are the assumptions that you tend to have to make in order? Sometimes these things are repetitive. If you are talking about, I mean, the process there usually there is a kind of a pattern. There is a trend that's developed. If you are doing this so many times, you'll find, I think you'll find that some of the assumptions are more likely to be made than others. So what are the assumptions that usually are made?
Yeah. Very good question, and a question actually that we are often struggling with. I'll say something about the process, and then I'll get to the assumption. So, what happens a lot is that we are asked to analyze a system for which some experimental results are available, and sometimes we make many assumptions, because to come up with an answer, and this answer very often says that 90% of the cost comes from this subsystem, and all the other subsystems contribute together combined 10%. So we start with many assumptions, and then I would say, to answer the question, is always we try to make fewer assumptions for the big drivers. So it's not always that it's the same. So thinking about a chemical facility, for example, sometimes separations are not that important. We try to approximate them, because even if we account for the details, it won't make a big difference in the result. And we try to dedicate more time in the big drivers, in the subsystems that are important. So I didn't answer the question. I know I described the principle, but this has served us well. And then once we understand the system, if the system gets to be improved through our collaborators, they do new experiments, they come up with new results. Now we realize this system is not expensive anymore, or is not important anymore. We will switch our attention to what's next. Let's say what's the next driver. So that's, I think, as a principle. In the past, we had made these big assumptions, for example, in the solar system that I described, that during the day, the sun is always shining. We don't go, for example, in the details, cloudy, non-cloudy. There are some control issues there. We always ignore this. I would say how we maintain the conditions for which we designed, we never really account for that. Yeah, I would say these are the major points.
Okay, thank you, Professor Maravelias. Any other questions, gentlemen? If there are no other questions, I'll take advantage and I'll ask my own questions. So, no else? Okay, so if that's the case, then let me ask two questions. So I actually appreciate the point that Dr. Ali Lawami from electrical engineering raised, and he's an optimization expert, and we always, here's the case, we always had a strong debate on how much should we simplify the process, right? And I'm a fundamental thermodynamicist, so I really keep arguing with him that we need to do the thermo and the kinetics pretty detailed. And it turns out from our calculations so far that it doesn't really matter, which is something that I don't want to admit usually. But from this background, this leads to my two questions, which are the first, both of them have to do with ammonia. The first one, did you apply the canonical surrogate unit models to ammonia synthesis processes?
No. So this was really equilibrium. Right? So we assumed that we reach, because these two reactions take place at different temperatures, and really we exploit the different equilibrium at the two different temperatures.
I guess I was talking about the, or maybe I was talking about the conversion, the slide where you had that you can approximate the conversion of the reactor through experimental data.
So in the solar part, we didn't use any experimental data. Everything was based on modeling. So for this reaction here, we are carrying it, let's say, at different temperatures when we are running the exothermic and the endothermic part, and we really take advantage of the move in the equilibrium.
Okay. Okay, I was talking about another slide, but still, this slide actually is good. So basically, you modeled the. I guess this is an ammonia decomposition to hydrogen, and you're using the idea is to use ammonia as a hydrogen carrier, correct? And you store this ammonia and then convert it later to hydrogen.
Yeah, so this is really in the loop, right? So this is what we're using inside the loop as the, let's say, instead of steam in our cycle. In one way, we are using the gases and then we go back. So this is not, we don't use hydrogen as a reactant. I mean, we do, but it's really part of the loop.
Okay, and you modeled that reaction just as an equilibrium, basically.
Yeah.
Reaction.
Yeah.
Okay. Okay. So then my last question is, and you really had a very nice case study on the electrochemical conversion of CO2 to methanol. Did you extend this case study to other methanol synthesis processes like?
We did Fischer-Tropsch. So I can very briefly say, and I can send you what we have done in that space. So Sandia National Labs contacted us and said, we have these new kind of prototype reactors. We can use them to split water or to split CO2. And we know that we can go to many different products. If we do that, can you help us understand, is it better to split CO2 to CO and oxygen? Is it better to split water? Should we be splitting both at the same time? So to kind of benchmark the space, we did different combinations of splitting CO2, water, and mixture, hybrid, and to two different products, methanol and Fischer-Tropsch. So once we have syngas, we can also go to Fischer-Tropsch products, let's say. So this is the, let's say, the analysis that we have done. We have not, I guess your question comes from the fact that once we are in methanol, then we can do many different things, right?
Yeah. Yeah.
We have not done that from methanol to olefins or methanol to others.
But actually, this is very interesting. So what was, if you can please share with us, what was the conclusion of the study?
Yeah.
Should they go with water splitting or CO2 splitting?
Yeah. So it's actually both. The best is obtained when you do both, because if you do one, very simplistically, you get let's say we do water, right? We get hydrogen, but then we have to start from CO2. We have to run kind of reverse water gas shift to get us to a good syngas composition, and there are some inefficiencies there. So if we split only one of the two, we need then water gas shift to get us to syngas, which we can do, right? We produce excess hydrogen plus CO2. We use some of it to give us CO. Plus the hydrogen, we do whatever we want. So the result was that if we can do both, and we can do both in two ways, we can have some systems dedicated to water splitting, some of them dedicated to CO2, or we can also do them together, right? Because at very high temperatures, both of will happen anyway. And then I'm talking too much, and I realize that we have passed the time. And then the Fischer-Tropsch is a little bit better than methanol. The challenge, which we made approximations, and is that we didn't really account for all the separations that would be needed at the exit of the Fischer-Tropsch reactor. We assumed that the value of what we get there, I don't remember the details, from C6 to C16, everything can go to diesel, but 80% of the price is not the final product that we can sell at a high price because we need some refining. So it was a little bit of an approximation there, but Fischer-Tropsch turned out to be a little bit better. But I can send you the references if you are interested.
Please.
Yeah.
No, definitely. I'm very interested, and I'll send you an email about it. So with that, thank you so much, Professor Maravelias, for this really exciting presentation and very nice work from you and from your group. And thank you everyone for attending today's seminar, and I hope you all have a good day.
Thank you very much, everyone, for taking the time late in the afternoon night.
You're welcome, Professor. You deserve it.